Alright guys, AP Physics C 2024 exam, set 2, question number 3. Let's see. This one says that there is a wire connected to a resistor of resistance R, okay, to form a rigid square loop of side length D. An external force is exerted on the loop so that the loop always moves with a constant speed V in the plus X direction. The loop enters the region 1 of external uniform magnetic field B that is directed towards plus Z, then plus Z. Here this is D, this is 2D. That's pretty much self-explanatory. This ends at 3.5D, and point S is the midpoint of the leading edge of the loop. Okay. Okay, all right. On the following axis, sketch a graph of the magnitude of the flux through the square loop as a function of position S, of position X of point S from 0 to 4.5D, and the plus Z direction of the flux is to be taken as plus positive flux. So I know that the flux is always positive because the magnetic field is always out of the page. So that's for sure. Now, the moment I start from 0 to D, and we have to find, we have to look for the flux of S. So obviously, S goes from 0 to D when there is no flux, because obviously in this region there is no magnetic field. So let me take this entire thing over on the other page so that it will be a little easy for us. Okay, so I was saying that from 0 to D, there is no flux, so the flux is going to be 0 over here, something like this. Then the moment it enters D and then it goes to 2D, obviously the loop will be completely here once it enters. And in this case, the flux, I think, linearly increases. Why am I saying that? Because flux is B dot A. B is B, whatever that is. Area will be this side, height, which is D, times whatever has penetrated inside. So whatever has penetrated inside is, let's say, X. So this is X over here. So the flux is going to be B dx. So definitely the flux is proportional to the distance traveled, right? So it will be a linear straight line till what point? D, sorry, 2D. So that's going to be like this. Okay. After 2D, something interesting is going to happen because some portion of the graph will enter of the coil will enter the other magnetic region, the region number 2, and some will still be in region 1. So I think it will still increase, right? Yeah, it should still increase. And till what point should it increase? Till 3D, because after 3D, when the S reaches 3D, this entire loop is in region 2. So there is no more increase because, then it's just a constant magnetic field. So I know that from 3D to 3.5D, that's going to be constant. So from 3D to 3.5D, let's say from 3D, in fact, let me make it this a little bit less steep. Uh, Perhaps something like this. Because when I go in region 2, I think it's going to be a little more steep. Yeah, because it's entering a region which is, which has a higher magnetic field. Yeah, because the magnetic field is exactly 2 times. So to be more precise, it should just be double of it. So at 2D, it should hold and it should tilt upward, towards a more steep curve. So I think it should go something like this. So there should be an evident tilt over here, which is more steep. From 3D to 4D, we already agree. Sorry, from 3D to 3.5D, we already agreed that there is no change in the flux. So the flux is going to be constant. And then after that, the loop starts coming out. We have to make till 4.5D. So till 4.5D, of course, the entire loop will be out of the magnetic field. So the flux will drop to 0 linearly, of course. So then we'll make a linear drop curve up, something like this. So that's going to be I think this is how the flux should look like. Okay. Consider the instant when point S reached 1.5 D. So I think I again have to borrow this. Okay, when point S is at 1.5 D, 1.5 D is over here. So it means that half inside, half outside. Okay, all right. What do we have to do here? Indicate whether the current is induced in the that is induced in the point S is clockwise, counterclockwise, or zero. That's pretty straightforward, right? Because we know that as per the Lenz's law, this is how the square loop looks like, and as per the Lenz's law, the current should oppose the cause, right? And in order to oppose the cause is the increasing magnetic field out of the page. So the current should be induced in such a way that it should induce a magnetic field into the page. And to make it into the page, the current should be clockwise in nature, because as per the right hand rule, right hand curl rule, right hand curl rule. We take our right hand and curl our fingers in the clockwise sense, so the thumb points into the page, which is what we need. So it has to be in the clockwise sense so that it can counter the increasing flux as per the Lenz's law. So right hand curl rule and Lenz's law. These are the two important reasons. Okay. Derive an expression for the current IS when the S reaches 1.5 D. If IS is 0, indicate how the derived expression. Okay, all right. So we have to derive the current in this case. So we can do that. Uh, the situation is again going to look like this, that as soon as the loop enters the magnetic field, let's say the loop goes in by X, so the magnetic flux is going to be B dot A. Once again, I'm just interested in the magnitude, so dot product as in cos 0 or cos 180 doesn't really matter because it will just change the sign, plus or minus, and we are not interested in that. So BA, area is D times X, so this is the flux. And what is the EMF magnitude? EMF magnitude is d phi over dt. So d phi over dt will make d over dt of b dx of b dx. B and d comes out because these are constants, and we are left with dx over dt. And what is dx over dt? Isn't dx over dt just v? Because dx over dt is the velocity, right? So we are just going to replace that with b dv. But what do they need? I don't think so. They need this, right? They need the current. So the current is going to be IR, IS is going to be the EMF divided, induced EMF divided by resistor. So it will be B dV over R, B dV over R. So that will be IS. So that's how it looks like. Okay. Write an expression for the power be dissipated by the resistor when point S reaches 1.5 D. Express your answer in terms of this. Okay, that's pretty straightforward because we know that the induced power will be the induced current, which is IS. We already found that, square times R. And what is IS? IS is BVD over, or BDV over R, BDV over R whole square times R. So it will be B square D square V square over R square times R, which is nothing but B square D square V square over R. That is the induced power. All right, let's talk about this question. So here we have the total energy dissipated by the resistor in the square loop S from 0 to 4.5 D is E original. Now, if the boundary shifted to 2.5 D, it means that there is more of region 1 and the new energy is E new. So how do we compare? Now, see, energy is after all dependent on power, and power is dependent on induced current. Induced current is dependent on induced voltage or induced EMF, EMF induced. And induced EMF is based on change of flux or d phi over dt. So more is d phi over dt, more will be the induced EMF. Now, it looks like the overall d phi over dt has decreased, but notice this carefully. Initially also, in fact, this image will give more sense. Initially also, from D to 2D, there was, this was region 1 and this was region 2. So if we are thinking that the excess of region 2 is now given as excess of region 1, don't you guys think that there is no change in the EMF here? I mean, there is no change anyway. So whether this constant flux is in region 2 or region 1, it doesn't make any sense. There's no upside to it because it's not adding up to the extra change. So it's same, right? Even though you increase the region 1 now, the flux initially, sorry, this one, the flux initially was where the flux is changing is this much. Now from here to here, anyway, the flux is not changing. So it doesn't matter whether it's in region 2 or region 1, there's no flux, change of flux. So EMF induced will not depend on it, and hence E new and E original are equal. All right. The last question which we have is, the original magnetic fields are modified such that now there is only single magnetic field, and now there's a triangular loop with resistance R here, and we have to sketch the graph of the induced current of point S as it moves from D to 3D. Okay, one thing is for sure, that the only change is when the graph penetrates inside, like this one. Once the graph, sorry, the loop, I mean, once the loop completely penetrates, to move from 2D to 3D, there is no change. There is no change in the EMF, right? Sorry, there's no change in the flux. So if there is no change in the flux, there is no EMF induced. So there is no current. So we know that from 2D to 3D, the current is going to be 0. Okay. What about the entering part? So the entering part will look like this. Let's say this was a triangle, and this has been entered now. So let's say this much portion has been entered into the magnetic field. Oh, sorry, the magnetic field is out of the page. So let's say this is how it works. Okay. Now this is D already, right? But we need to find this area over here, because we need to, after all, find the area so that we can find flux and so that we can find the change as well. Uh, Now, let's say this is Y, and we know that this was also D. So they are in the same proportion. That's something which we know. So if this is Y, this has to be Y as well, as per the properties of symmetric triangles. So this is Y, this is Y. So what is this area? We know that the total triangle area is half times D square. And the small triangles area, this triangles area, uh, this triangle's area is going to be, in fact, why am I taking as y? I think it will make more sense to take as x to avoid confusion. Let me just take it as x, because there's no y-axis involved here. This area will be half x square. So the shaded area is going to be half d square minus half x square. So the flux is going to be BA, and A is half d square minus half x square. So the EMF, which is d phi over dt, is going to be B times 0 minus 1 over 2 times 2x dx over dt. Okay. Do we have to form the magnitude? It looks like that because they are just indicating the plus axis. So EMF is going to be, just ignore the negative sign. It will be minus bx dx over dt is v. So once we have bxv, this is the EMF. Now, a common pitfall is we might think that x increases from 0, but no. Notice this x, it actually increases, or maybe this x, this actually, and actually that x doesn't make doesn't make much sense. But yeah, this x increases from, or starts rather from D, right? The maximum length, and then eventually goes to 0. So it starts from the maximum value. This is the maximum value D, and then eventually this vertical length becomes 0 as it penetrates into the page. So this starts from a maximum value. Maximum value will be somewhere over here, and then eventually x becomes 0 when the loop completely penetrates into it, so it goes linearly down. And obviously 2D to 3D, that has to be 0 because there's no evident change in the area because the complete area is inside the magnetic field. So this is how it works. Let me know if you have any questions, and I'll see you in the next video. Bye.